Hello students, good morning. Welcome to my lecture on chapter number 10 Halogen derivatives, class 12 science, Maharashtra State Board New Syllabus 2020. In the previous lectures we have studied about preparation of haloalkane as well as preparation of haloarenes. Today we are going to study physical properties of halogen derivatives. See, let us study physical properties. Alkyl halide, they are represented by Rx, where R is alkyl group and X is halogen. They may be fluorine, chlorine, bromine, and iodine. Alkane, they are represented by RH. R means alkyl group, H means hydrogen. Let us see the example. CH3, CH2Cl, that is ethyl chloride. It is what? Ethane. See, physical properties of alkyl halide are different than those of alkane. Reason behind it is, see here, both the carbon atoms, they don't have any charge separation, so it is what? Non-polar. Ethane molecule is what? Non-polar, or alkanes are non-polar. But alkyl halide, see, RH, X carries negative charge and R carries partial positive charge. Similarly here, this carries negative charge and this carries what? Positive charge. Okay, so these are what? Polar. Okay, and because of this polarity, alkyl halide shows different properties than those of alkene. You know that physical properties, they may be density, solubility, melting point, boiling point, stability, etc. So let us start with nature of intermolecular forces. Nature, see, we have X. Now halogens, that is what? F, Cl, Br and R. These are what? Halogens. They are shown by what? X. Halogens are more electronegative than that of carbon, and therefore this halogen acquires partial negative charge and carbons acquire partial positive charge. You know the reason, that halogens are more electronegative than carbon. So carbon acquires partial positive charge and halogen acquires partial negative charge. And due to this reason, alkyl halides are polar in nature. Polar in nature. Now, one thing we have to study here, this bond, CX bond, is polar covalent bond. Why is it called polar covalent bond? First of all, carbon and halogens, they are non-metals and they can form a bond between them by sharing of electrons. Therefore, the bond between C and X is what? Covalent bond. But there is a charge separation. See, X is electronegative than carbon, so X acquires, or halogen acquires partial negative charge and carbon acquires partial positive charge. So they show what? polar nature. So bond between carbon and halogen is called as what? Polar covalent bond. Now we are going to study this table in detail. But before that, you remember this relation: bond strength directly proportional to bond enthalpy and bond strength is inversely proportional to bond length. Now come to group number 17 elements. Group number 17 elements denotes halogens like fluorine, chlorine, bromine and iodine. You know that in fluorine they have 2p orbital, chlorine they have 3p orbital, bromine they have 4p orbital and iodine they have 5p orbital. From this you know that fluorine have small size and iodine have bigger size. Okay, fluorine have what? Small size and here iodine has large size, because size of the p orbital increases down the group from fluorine to iodine. Now what happens? See, consider this Cl, then consider CCl, then CBr, then consider Cr, whose is small, and for Ci bond length is bigger. Okay, you remember one thing, that is smaller the bond length, stronger is the bond. This point is very important. Smaller the bond length and stronger is the bond. So for Cl, bond is strong, and for this bond is weak. See, and you know that bond length means what? The distance between nuclei of two atoms. That is what bond length. If you consider Ca, bond length is small, and for Ca bond length is more. And what is meant by bond enthalpy? Bond enthalpy means what? Amount of energy required to break 1 mole of covalent bond is called as what? Bond enthalpy. Now come to this table. For CH3F, bond length is 139 pm. It is very short and it requires more amount of energy, that is 452 kilojoule per mole. That is called as what? Bond enthalpy for CF bond. Come to this iodine, come to this methyl iodide. Here bond length is bigger, so bond is big and it requires less bond enthalpy, that is only 234. According to that, see that for CF bond length is what? 139. For CH3Cl bond length is 178, so it requires bond enthalpy 351. Similarly for CH3Br, bond length is 193 picometer and bond enthalpy is 293. Means as you down the group, down the table, bond length goes on increasing and here bond enthalpy goes on what? Decreasing. Now come to next point, that is dipole moment. Dipole moment is shown by mu is equal to Q into what? R. Here mu means dipole moment and Q is what? Charge present on the both the atoms, and R represents distance between the covalently bonded atoms. Now see here for CF dipole moment is 1.847 and for CCl dipole moment is 1.860, and for CBr it is 1.830, and for this you have for Cr dipole moment is what 1.636. Okay. Now see, there is a very little difference between dipole moment of Cf and dipole moment of CCl, because the dominating factor is what? Q. Dominating factor of dipole moment is what? Q. Q means what? Charge. You know that for fluorine and chlorine there is no difference in the charges. So here R affect the value of dipole moment for Cf and CCl, because for Cf bond length is small and for CCl bond length is more, and therefore dipole moment of CCl bond is what? Greater, and for Cf it is smaller. Means bond strength is directly proportional to bond enthalpy and inversely proportional to bond length. You remember this relation, it is very important. Now come to boiling point. You know that boiling point is the temperature at which vapor pressure of liquid becomes equal to its atmospheric pressure. That definition already we have studied in 11th standard. But generally, if you consider water, boiling point of water is what? 100 degrees Celsius. In Kelvin, it is called 373 Kelvin. Means at 373 Kelvin, water boils. Now come to alkyl halide. See, I have written some alkyl halides along with their boiling point. See this table. Methyl CH2A boiling point 194.6 Kelvin. I have considered here same alkyl. See, I have taken methyl chloride, methyl bromide, and methyl iodide. What happens? See, boiling point goes on increasing. What is the reason behind this? See, for this table, boiling point is directly proportional to size of halogen atom. Size of halogen atom. As size of halogen atom increases, boiling point goes on increasing. I understood. I hope you understood this point. That is what for this table boiling point is directly proportional to size of halogen atom. Okay. Now come to second table for same halogen. I have considered same halogen. That is what? Chlorine. I have considered chlorine. See here methyl chloride, ethyl chloride, N-propyl chloride as well as N-butyl chloride. See, you know that there is only one carbon atom, there are two carbon atoms, there are three carbon atoms, and here there are four carbon atoms. For this, boiling point is proportional to number of carbon atoms, or you can say number of carbon atoms. Boiling point is directly proportional to what? Number of carbon atoms present in alkyl halide. Or we can say boiling point in general, boiling point is directly proportional to molecular mass. As you know, number of carbon atoms are increases, molecular mass also goes on increasing, and therefore see here for methyl chloride boiling point is 248.8 Kelvin, for ethyl chloride it is 285.5 Kelvin, and for N-propyl chloride it is 320 Kelvin, and for N-butyl chloride it is 351.5 Kelvin. Remember this, but there are some exceptions that we will do. Now come to this point, that is for isomeric alkyl halides we have to study boiling points. You remember 2 points, they are very important. First one is what? Surface area. Surface area is directly proportional to van der Walls forces. Van der Waals force. Similarly, surface area is inversely proportional to what? Branching. And this surface area directly proportional to what? Boiling point. Or we can say van der Waals forces directly proportional to boiling point. Now see, there are some relations, you have to remember this. Now see, for isomeric alkyl halide, for N-butyl bromide, boiling point is 375 Kelvin, and for secondary butyl bromide, boiling point is 364 Kelvin, and for tertiary butyl bromide, boiling point is 346 Kelvin. From this table, see that boiling point goes on decreasing. So we have to study the reason behind this. For this N-butyl bromide, see this relation. Surface area is more, so van der Waals force is more, and therefore boiling point is more. According to this reason, van der Waals force is more, boiling point is more. But for this, see what happens here. One branch is there, and therefore that branch affect the packing of the secondary butyl bromide, and therefore branching reduces the surface area. So boiling point goes on decreasing. For this, it is what? 364 Kelvin. Again, come to tertiary butyl bromide. Here there are two branches. So again, surface area goes on decreasing, and therefore packing is very difficult, and therefore boiling point of tertiary butyl bromide goes on decreasing. That is what? 346 Kelvin, because less surface area, then less van der Waals forces, so it requires less energy to break, and therefore boiling point is what? 346 Kelvin. I hope you understood this concept. Go through that, you remember these points properly. Now come to the next property of halogen derivative, that is solubility. So you know that alkyl halide, see, it is R positive, partial positive, X partial negative. There is one more alkyl halide, partial positive, partial negative. The attraction between these two molecules is what? See, it is dipole, it is also dipole. So this attraction is called as what? Dipole interaction. Okay, and you know that alkyl halide is what? Polar in nature, that already we have studied. Now come to water. Now see, in water, this water molecule, this attraction is called as what? Hydrogen bonding. And see, this attraction, we are going to study two molecules, alkyl halide as well as water. You know that alkyl halides being polar are insoluble in water, insoluble, or you can say immiscible. in water but soluble or miscible in organic solvent. This is because alkyl halides are not able to form hydrogen bonding with water. Here what happens? Rx see, this is dipole and this is also dipole, but this dipole-dipole interaction is weaker than this dipole-dipole interaction, but here hydrogen bonding is more stronger than this, and therefore alkyl halides are insoluble in water but soluble in organic solvent. That is what light dissolves in light dissolves light, because see, alkyl halide is a covalent molecule as well as organic solvent, they are also covalent. So alkyl halides are soluble in what? Organic solvent like acetone, alcohol, etc. And therefore alkyl halides are insoluble in water. And simply you can say alkyl halides are not able to form hydrogen bonding because attraction between alkyl halide molecule is more stronger than this. Now you know that aryl halides are also insoluble in water but soluble in organic solvent. See this example. See, it is what? Ortho dichlorobenzene. It is meta dichlorobenzene and it is para dichlorobenzene. See here, boiling point they have almost the same. See, for this 453 Kelvin, for meta 446 Kelvin, and for para it is 448 Kelvin. But first of all, you remember this is what? Polar, and this is what? Non-polar. Why like this? See, use this angle. See this angle. We consider it is what? Theta. This theta is proportional to polarity or dipole moment. Dipole moment see, theta is inversely proportional to what? Dipole moment, and therefore this is what? Polar. It is more polar than this one. Bond angle is more. Here bond angle is what? More. So it is what? It is also polar. Now see here, bond angle is what? Maximum. So it is what? Non-polar. And therefore the boiling point is nearly same for all these compounds. See, there is a little difference, 446 and 448 Kelvin. It is because of this what? This theta, because it is polar and it is non-polar. Okay. Now come to melting point. Melting point, see, for para dichlorobenzene melting point is maximum. See, for melting point you remember 2 points. One is what? Intermolecular forces. And second one is what? Lattice structure. These 2 points affect the melting point. Lattice structure may be what? SCC, BCC, FCC, etc. Okay. Now, see here, para dichlorobenzene is symmetrical. It is what? Symmetrical. And therefore, these molecules, they are closely packed and therefore they have more melting point as compared to orthodichlorobenzene and meta-dichlorobenzene. So these are what? Higher melting point. I hope you understood all this concept. Now we have completed physical properties of halogen derivatives.